Hello all, my name is Matt Dennis, and this is our Senior Design Team 2033's Inverted Pendulum Robot video demonstration. My partner Joe and I will take you through our design and discuss its importance, as well as what we think can be learned from our work. We would like to start by thanking Dr. Zhang for his consistent leadership and guidance this summer. We would not have been able to do this without him, so thank you. Here we have our project statement, with a picture of our robot to the right. The main goal that we set for this project was to have a fully functioning robot with interactive capabilities. We did not want to simply build a robot that worked, but we were motivated by the students who would learn from it. As we know, engineering is an extensive and expanding field with endless possibilities, and with it we are able to change the world and create a brighter future for all. The first step for us as engineering students is to look back and introduce some of the same concepts that got us on the path of STEM to those who are learning about career options. That is why we have designed our robot to be used by the University of Connecticut's Electrical and Computer Engineering Department for community outreach. By demonstrating concepts such as physics and robotics, we can inspire the next generation of engineers, leading students to continue to design the future. Uconn has many organizations on campus that visit local grade schools and perform demonstrations with these students. The objective of our project is to create an inverted pendulum robot for the electrical engineering department to use during these visits. Our design demonstrates core electrical engineering principles through physics, systems control, and robotics, while having the option to be interactive to further spark the interest of these students. This is a detailed look at our design. We had to make various changes to it as we went through the build in order to make it more user-friendly. On the right you can see our original design as compared to our final product in the center. The major components of our robot are the Arduino microcontroller as the brain, our power switches circuit, a motor driver to send signals to the two motors, and an IMU, or inertial measurement unit, to keep track of where the robot is positioned. This was one of our first successful attempts. You can see the robot stabilizing itself and reacting to any outside forces Joe applied to it. But when he applied too much, the robot flops right over. After a few days of tweaking the code, we were able to get a solid performance out of our robot. You can see here when Joe moves the cord from his computer to the robot, it begins to measure the new moment of inertia and correct itself to stay standing upright, even after he gives it a few taps. One of the key elements of our design was the use of Legos. Knowing that this was going to be used for school demos, we wanted to be sure that some element of the robot would be very familiar to the students, as well as interactive. The robot design itself is quite interactive, as you can see, but the addition of Legos will allow for students to build upon it and adjust it in real time. As we became more confident with the robot's performance, we added a Bluetooth component which allows for your phone to act as a controller. Here's a clip of Joe showing how it works.
It works. I'm turning it left and right. Stabilized. Yeah. You just have to be like really careful moving it forward and back. Like quick taps. Give it enough time for it to balance itself out. Cause it's moving backwards like fast.
Here's one last clip of Joe showing how the robot operates from start to finish. He starts by uploading the code, making sure to hold the robot upright so the system is able to zero out. You can see here that it goes off center as the code finishes uploading, and the system tries frantically to find a stable point. Joe then resets the robot's positioning, and the system slowly adapts and becomes more stable. Joe then turns on the Bluetooth adapter, unplugs the USB cable, and begins sending signals to the robot. The robot does not immediately respond to his inputs and continues to search for a stable point, and then becomes overwhelmed with instructions and topples over. Immediately he sets it upright, plugs the USB adapter back into his computer, ensures that he turns off the Bluetooth port so that no lagging signals interfere with the controller, and begins to re-upload the code so that he can try again. Normal senior design teams have a full 30 weeks or 2 semesters to design, build, and test their projects before their completion. But in our case, we had 11 short weeks during the COVID-19 summer of 2020 to do all the same. In the end, we were happy with our design and how it worked, but we know that there are some things that can be improved upon. To start, both Joe and myself are electrical engineers who have limited knowledge when it comes to code, so we know that it can be reworked and have a more streamlined solution. Along with that are the sensor calibration and the tuning of the controller gains. We did as best we could with a limited time, but most projects that we saw similar to ours took a few months just to tune the gains to achieve a perfectly stable system. We also know that we can make the robot much lighter by decreasing the size of the battery. The 22.2 volt power source that we used would last for almost a day and a half at full charge, much longer than any demo would need to be. We hope that this design will be reworked by other engineering students to complete our design and carry out their own journey as up-and-coming engineers. From Irizarry, Dr. Zhang, and myself, thank you all for watching and continue to redesign your own future.